Hello everyone, my name is Mohammad Jaberizadeh. I'm a PhD student at the University of Texas at Arlington. It's a pleasure for me to present my research entitled as Sustainable and Eco-Efficient Cementitious Composites Using Waste Cellulose Fibers. Well, speaking of cellulose fibers, these are produced in different dimensions from nano to macro scale that they have a unique molecular structure composed of polymeric chains of lignin, cellulose, and hemicellulose that give these fibers outstanding intrinsic properties such as high tensile strength, low thermal conductivity, lightweight, and high water retention and release capacity. To those, I should add economical and environmental advantages that make these fibers advantageous to be used for producing fiber-reinforced composites. However, effectively using these fibers in construction materials require certain challenges to be addressed. For example, they need to be effectively dispersed to avoid agglomeration, and they should be protected in highly alkaline environments from disintegration. A great source of these fibers are agricultural waste that are often incinerated within the agricultural industry with detrimental impact on the environment due to the emission of carbon dioxide. To reduce the emission of carbon dioxide and address the environmental issues associated with that, we use these fibers to produce eco-efficient concrete with enhanced mechanical and shrinkage performances. As you can see in the right side of the slide, these fibers also have a substantially lower carbon footprint compared to the most common types of fibers that are used for producing fiber-reinforced composites. Most specifically, compared to the conventional cellulose fibers, these fibers have a lower carbon footprint, on average about 76%, that adds to the importance of these fibers to be used for producing fiber-reinforced composites. With that said, in this presentation, I will show you the results of our characterization of pulped Vitestra, which we used as our waste cellulose fibers, followed by the dispersion technique that we applied on these fibers. Then I will continue with their effect on the microstructure, how these fibers affect the hydration reactions and hydration products. Then I will continue with the effects of these fibers on the autogenous shrinkage of WCF mortars and their mechanical properties at different dosages. Next, I will continue with the protective approach which we used to for the integrity of these fibers, which was carbonation curing, and I will wrap up my talk by presenting the main conclusions. In case of characterization, polymeric chains of these fibers consist of both amorphous and crystalline regions in their molecular structure. Crystallinity index is referred to as an indication of the relative amount of crystalline regions in the molecular structure of these fibers that along with the amount of cellulose and hemicellulose that they have can determine their various properties, including mechanical properties and thermal behavior. For determination of crystallinity index, I used a peak height method using XRD spectrum that resulted in a CI equal to nearly 60%, suggesting the presence of amorphous regions in the molecular structure of these fibers. Also using TGA, we quantified the amount of cellulose and hemicellulose, which was nearly 19%. Next, another property of interest is the amount of water that these fibers can absorb, because the magnitude of reductions in the autogenous shrinkage is a function of the moisture that is supplied by these fibers to activate internal curing mechanism and reduce the internal stresses caused by self-desiccation mechanism. For determining water retention capacity, I use the standard centrifugation technique such that a certain amount of fibers is soaked in water, left to be fully saturated, and then their mass after centrifugation was periodically recorded while being oven dried. And based on our measurements, these fibers could successfully absorb nearly 10 times their weight and release it in approximately 11 days. In case of dispersion, as I said, the effective use of these fibers require a successful dispersion to avoid agglomeration. We used shear mixing as our dispersion technique, and zeta potential experiment was conducted on the suspension of these fibers to evaluate the quality of dispersion. We applied this on the suspension of as-received fibers and resulted in a polymodal distribution of zeta potential values due to the heterogeneity of surface charges that results in a suspension with unstable suspension. To overcome this issue, I followed the dispersion technique patented by Professor Shah and Professor Kansta using surfactants that resulted in a monomodal distribution of zeta potential values that led us to a suspension with improved stability that is suitable to be used in construction materials. Following our experiments, I used isothermal calorimetry to determine the rate of heat evolution of hydration reactions for both plain cement and WCF paste. And as you can see, similar rate of hydration reactions is observed for both mixes, but the WCF could reduce the peak intensity of heat evolution due to the lower thermal conductivity of these fibers that reduces the heat flow of the material. Also, I used thermal gravimetric analysis to quantify the hydration products, namely bound water and calcium hydroxide, that according to our results at different ages, the difference between these two products was less than 1%. That shows that incorporation of these fibers didn't change the quantity of hydration products. Now, that we are confident that using these fibers, the hydration reactions and products are not affected. We are confident to proceed with their evaluation on the macrostructural performance. Starting with autogenous shrinkage, I measured the autogenous deformation of WCF mortars at a very low water to cement ratio at different dosages that led to significant reductions of autogenous deformation at up to 60% for our 0.25 weight percent of cement sample at up to after 7 days of hydration. Then next is the mechanical properties. In the case of this property, I used linear elastic fracture mechanics that to plot the applied load versus the crack mouth opening displacement, and using the peak load of this curve, I plotted the development of flexural strength on the right of the slide, and there you can see that a WCF mortar surpasses that of the plain mortar, especially at the early ages, showcasing of at least 20% enhancement. Using the same graph, I calculated the area under these two curves to determine the post-crack flexural toughness at different deflection points. Followingly, up to 49% enhancement was achieved that indicates the superior energy absorption capacity of WCF mortars. Extending our mechanical testing to 56 days, we noticed a reduction in the mechanical properties such that the load CMOD curve of the WCF mortar at 56 days falls below the load CMOD of the same mix at 28 days. Using a scanning electron microscopy, I noticed that these fibers have undergone disintegration. And also, after they release the absorbed water, they shrunk, and a loss in the interfacial adhesion is observed. Both of these phenomena can explain the reductions in the mechanical properties and must be addressed to preserve the long-term mechanical properties and overall performance of the composites. The conventional protective measures include using supplementary cementitious materials to modify the matrix or modify the cellulose fibers themselves through different chemical treatment procedures. Although both of these methods are effective in enhancing the durability of the fibers, there are some disadvantages. Most specifically, these fibers the loss in the interfacial adhesion occurs at the later ages. So the effect of these methods is not very much clear to us on the interfacial adhesion. Instead, our focus turned to the exploration of carbonation curing, which is an environmentally beneficial approach that repurposes carbon dioxide. This way, carbon dioxide penetrates within the pore structure of the material and reacts with hydrated and anhydrous phases of cement to produce calcium carbonate. This recently generated calcium carbonate serves to occupy the gaps between the fibers and the matrix to improve the interfacial adhesion as well as protecting the fibers from disintegration. Our SCM observations proves this such that the loss in the interfacial adhesion in a moist pure sample is completely filled with products after carbonation curing that results in improvements in mechanical properties. You can see here for compressive strength and flexural strength, especially at 28 days, we have reductions in the mechanical properties for moist pure samples. That is completely compensated for after carbonation curing, resulting in 25% enhancements for compressive strength and 43% improvements for flexural strength. Having the modulus of elasticity calculated for carbonation cured samples, not only the results did not decrease, but also 55% enhancement was observed for the corresponding moist cured specimen. In conclusion, using waste cellulose fibers, I produced eco-efficient composites with enhanced mechanical and shrinkage performance and lower carbon footprint and cost of composite production. According to our results, a monomodal distribution of zeta potential values was observed that resulted in a suspension with improved stability. Also, because of the high water retention capacity of the fibers that could mitigate the internal curing internal stresses caused by self-desiccation mechanism, significant reductions in the autogenous shrinkage values up to 65% was observed. In terms of mechanical properties, using WCF, we could enhance the flexural strength and energy absorption capacity up to 25% and 50% respectively, especially at the early ages. And to preserve the long-term mechanical properties, we had to protect the fibers, and we applied carbonation curing as our protective method that resulted in improved interfacial adhesion and enhanced mechanical properties. Of course, there are a lot of other properties to check. That's why we are here in the research in progress. And these days, we know that these fibers can enhance the carbon uptake, and that's what I am investigating in my research. At the end, I would like to appreciate my advisors, Professor Shah and Professor Konstal, and my colleagues at the Center for Advanced Construction Materials. I would like also to extend my gratitude to USDOT for financial support of our Tier 1 University Transportation Center for durable and resilient transportation infrastructure. I would be more than happy to address any questions.